This is Jenny Kunkel, and in this video we're going to take a look at data types. We are covering this in Chapter 8 of Murach's SQL Server 2022 textbook. We are going to expand our discussion to include the ANSI standard with Oracle as well, and we can take a look at what this means. Now, why we're studying this week is because we will be starting to look at logical design next week and then physical design, and we'll certainly be using data types when we get into our physical design of our tables, and we're just a couple weeks away from that. So it makes sense that we get a good understanding of what types are available, what they mean with respect to potentially the storage that's involved, so we can make informed decisions when we're trying to identify what types of data we need to define with their corresponding types when we are creating our tables. To get started, if we look at our ANSI standard, we have a character. This is going to be a fixed length character string, and pretty much across the board, SQL Server and Oracle both support the char. We have the varchar, which is the ANSI standard, and both support it, although Oracle is using the varchar2 instead of the varchar for the variable length character string. And we'll get into the difference between the fixed length and the character strings in just a little bit. We also have the national character varying, and this is supported by the nvarchar and the nvarchar2. Now, what does that mean? So we have variable lengths of Unicode. So that means that if we have some Chinese characters, we can store that in an nvarchar where we couldn't store it in the varchar. And that's because with our Unicode, it requires more bytes for storage than our varchar data type allows. Next, we have the national character. This is going to be the cousin of the char above, but this is going to be for the fixed length Unicode string, and this is supported both by SQL Server and for Oracle. Then we get into the big int, integer, and small int. They're supported by SQL Server. However, Oracle is using its base data type for numbers, and that's going to be the number, and it's going to have a precision of 38 with a scale of 0. So the second value is going to be 0. If you do not provide a second value, it's going to assume 0. This is going to be for the 64-bit integer, the 32-bit integer, and the 16-bit integer. Then the next ANSI standard is real. That's supported by SQL Server. For Oracle, it's implemented as a binary float, which means it's essentially defined as a float 63. That's going to reflect the 32-bit floating point. For the float, it's going to be supported by SQL Server, but for Oracle, it's going to use a binary double, and that's going to be the 64-bit floating point. Moving on to the next slide of data types, we have the decimal with a p, s. We kind of alluded to this before. We have a precision and a scale. We'll get into another example in just a little bit and define what the precision and scale is. But for SQL Server, we have the decimal defined and implemented. We have the number, which is Oracle's base type, with the precision and scale for the fixed precision decimal. For the ANSI standard Boolean, this is supported by the bit in SQL Server, which you can store a 1 or a 0. With Oracle, we would need to use the number data type, define it with a precision of 1 and a scale of 0. We would additionally need to implement a check constraint to make sure that we would only be allowed to store 0 and 1 in that column. With our dates, the ANSI standard is supported in SQL Server. It is also supported in Oracle, but in Oracle, it also stores the time. In a lot of cases, when we're tracking activity in Oracle databases, we use the date to define the type, not the timestamp, which we'll see pretty soon can also store the date and the time component. With the time, this is implemented in SQL Server as time. We can store just the time in a timestamp. In Oracle, we can also store the date and the time in a timestamp in Oracle. That's where we get into a choice between the date and then the timestamp when we want to define those fields that need a date and time. Typically, it's been the custom historically to use the date. There are times that you would want to use the timestamp, but in most cases you want to use the date. Now with SQL Server, it's implemented as datetime2, so a little bit different there. Then we get into the blob, or var_binary. So this is for variable length binary storage. This is where if you had some type of a document that you wanted to store in the database, you could define it using a var_binary type. In SQL Server, that document would have to be pretty small in order to store it within the database. If you were going to try to store a large one, it would not succeed. You would have to use some type of different mechanism where it tracks file locations, and you would be storing it like on a file server somewhere in that case. So it gets a little different in that scenario. Now with Oracle, you can store large or small documents within the database. You can use the raw or the blob to do that. Then we're going into a couple different non-ANSI standard types. With SQL Server, you can define a large variable length text to use the maximum length of a varchar. The varchar max stores about 2 GB in length. The text can also be used as well for that large variable length text. With a clob, in Oracle, you can store almost 4 GB in that field. Then we get into our nvarchar max and our ntext and our nclobs. Those are supporting the Unicode versions of those large variable length text values. And then we have money for SQL Server. So if you need to define some type of value that's going to be used for money, typically in SQL Server we use money. In Oracle, you would use something, a large number like number 19,4, that's going to give you a lot of precision and scale for that number. Now moving on, we're going to go ahead and use one of our SQL Server slides to take a look at the difference between our fixed length, our char and nchar, to our variable length, varchar and nvarchar fields. If we look at the example, it's going to start with the char 2, and this is going to store then the CA, the abbreviation for California, and we can see that the value stored is CA, and the number of bytes that are used are 2. So each character that's being stored requires a single byte of storage. If we look at the char 10, each byte is going to require a single byte of storage. We have designated 10, therefore we're storing 10, irregardless of the fact that we only have CA as our value. It's still going to take up that 10 bytes of storage. On the reverse side, if we define something as varchar 20 and we store CA in that field, it's only going to take up the storage that's needed, so those 2 bytes to store CA, but then there's going to be a little bit of overhead in 2 bytes that is going to be used to keep track of how many bytes are actually stored there. So that number that's keeping track of it is going to take up 2 bytes to keep track of how many bytes are stored there. Now for our varchar 20, for storing New York, in this case, we have 8 bytes that it's being used, plus the 2 for the overhead, keeping track of the 8 bytes that are actually being stored. So that's going to require 10 bytes of storage. Now, if we were defining something and we wanted it so that we were just defining 2 bytes for our state abbreviations for all records, we would define that as a char and not a varchar, because if we look at it, we're only storing 2 bytes max. Maybe there's no values being stored there. We would have the 2 bytes of storage plus the overhead. We would be storing a lot more things and taking up more space with a varchar than if we were using the char. If we don't have any idea how much text that something is going to be entered into a particular field, if we define it with whatever the maximum is, it's better in that case to use a varchar as long as it's more than like 2 or 3 bytes, because at some point there's a trade-off there with that extra overhead bytes that are being stored. If we get into our nchar, for our nchar, every character that we store is going to take up 2 bytes of storage, even though it really only needs 1 byte. like in the case of CA, California being stored in that field, each of those characters is really a 1-byte character, but we're storing it as a Unicode, which means that we would be storing that upper byte with all zeros in it because it's not really being used, but it's still going to require that storage. So where we have an nchar of 2, it's going to essentially be double that, and we're going to be storing 4 bytes. Same with that nchar 10, it's going to be storing 20 bytes, even though we're not using all 20 bytes for that CA. And then when we get into our variable with the nchar, it's going to essentially do the same thing, but each of our bytes are going to be multiplied by 2. So CA is going to be 4, and then we have our 2 bytes of overhead, keeping track of the length of that string. So that's going to be 6, and then for New York, that's 8 bytes. And we have times 2 because each character is going to be 2 bytes, and that's going to be 16. And then we have that overhead byte that's keeping track of everything, so those 2 bytes there, and that would make it 18. So you can kind of start visualizing how much storage is being used. You can kind of understand if I'm creating a table that's going to be used in multiple languages, then you would probably want to use nvarchar for some of the large fields. If it was a very small field, maybe an nchar if it was like at 2 bytes. But for the most part, you're going to probably want to use the nvarchar in a lot of cases. For our defining of fields in the database, we use varchar and the nvarchar more than we would use the char. It would have to be where you just have a small amount of predefined values that you would want, that you're not going to be wasting storage. So you have to think about storage when you're defining the fields as well. Now on our last slide, what we're going to take a look at is an example of how we can define a table using the decimal and the number. Those were the 2 options for the decimal type. So essentially, Oracle's decimal precision is actually implemented with a number. And we can see that we're defining it with 10, 2, meaning that it has a precision of 10 and a scale of 2. But what does that precision mean? The precision is the total number of digits, and that includes the decimal places. So if I have 10 digits, I have 8 before the decimal place, and then I have 2 at the decimal place. So that's going to give me the 10 precision, and the scale is essentially going to tell me how many decimal places I have. So in this case, with 10, 2, I have 8 digits before the decimal place and 2 after the decimal place. Same with Oracle. When I have the number 10, 2, I have a precision of 10, meaning that I have a total number of 10 digits, 8 before the decimal place and 2 after the decimal place. So if we start thinking about if we're defining numbers that require decimal places, this would be the way to do that. Now, if we're dealing with money for SQL Server, we're going to use money instead of using a decimal. But with Oracle, we would still be using that number with the precision and scale. We would want to make sure that we would have the correct scale and the correct precision to hold the entire number within it. Typically, when you get into having some numbers and there could be rounding or whatever, you are storing something like 4 or 5 scale digits, and then that's going to be then compensated within the total precision of the field as well. So hopefully that makes a little bit of sense, and we can understand a little bit more about our data types that can be used when we get into our physical design.